In this video, we're going to cover the fundamental theorem of calculus, or FTC. And by the way, most of these notes are found in your Cycle 3 packet, starting on page 19. So let's take a look at a few examples first. Step 1 says determine, and this is capital letter F of x as a function of x. And of course, when you see that capital letter, you know you're going to be taking the antiderivative. And then in step 2, we're going to determine the derivative of the antiderivative. All right, so here's step 1. The antiderivative of this function would give me t cubed over 3, and then we evaluate that from x to 0. If I were to substitute in x, that would just give me x cubed over 3, and then if I substitute in 0, 0 cubed over 3, and when I clean that up, that would just give me x cubed over 3. So that's step 1. That's the antiderivative. Now, in step 2, it wants me to find the derivative of that. And so if I find the derivative using the power rule, that would give me, well, 3x squared over 3. And those 3's would cancel, and I'd have x squared. And so what we're going to look at is see if we can recognize the pattern between the original problem and our answer. All right, let's take a look at our second example. Step 1, let's find the antiderivative. So that would give me t cubed over 3 plus 4t squared over 2. And I'll clean that up just a little bit, just to give me a little more workspace. All right, now we're going to evaluate that from x to 1. So let's sub in the x first. So that's going to give me x cubed over 3 plus 2x squared. And then we're going to subtract the function evaluated at 1. So that would just give me 1 cubed over 3, or 1/3. And then I need to subtract this whole thing, so I'm going to add in a parenthesis here, and then plug in a 1 here, so that would just give me 2 times 1, which is 2. So anyway, when we do our step 2, what you'll notice is that this is just a constant, and the derivative of a constant is going to go to 0. And so I'm really not even going to pay attention to the evaluating at that lower limit, so long as the lower limit is a constant. All right, so now we're going to take the derivative of this. And so if I use the power rule, let's see, that would give me 3x squared over 3 plus 4x. And if I cleaned up the 3's, I have x squared plus 4x. And again, notice the relationship between the original function and what our result is. In problem number 3, first step, I'm going to do is rewrite it. So t to the 1/2 dt. So then the antiderivative would be what? Let's see. T to the 3/2 divided by 3/2, or multiplying by 2/3. And we're going to evaluate that from x to 5. And so this would be 2/3 x to the 3/2 minus 2/3 and then 5 to the 3/2. Again, all of this is going to be a constant, so when I take the derivative in step 2, it's going to go away. So if I take the derivative of just that first term, though, 3/2 and 2/3 are going to multiply to 1, so I will just end up with x, and then if I subtract 1 from the exponent, that's just 1/2, which is just the square root of x, which is what we've got here. One last example. All right, so the antiderivative of sine, well, I believe that would be what, negative cosine? Yes, negative cosine. And then evaluate, oh, I should put a t or an x, and then evaluate it from x to 1. And that's why we have the t. It's just so we're not confusing the same variable. Why are we substituting in an x for an x? It should be t. And then this is x and 1. All right, so then this would be negative cosine of x minus, and then negative cosine of 1. This is a constant. The derivative will go to 0. So in step 2, we need the derivative of negative cosine, which would be a derivative of cosine is negative sine, so a double negative, which would give you just sine. All right, and that's what we ended up with. Okay, so without the two-step process, did you notice what was happening? We were just evaluating the function at x. That's it. So if I have f of x and it is the integral from some constant to x of, in this case, our function is t to the 7th dt, then f prime of x is just going to give me, well, x to the 7th. In the second one, if f of x is equal to the integral from -1 to x, again, -1 is just a constant of this square root of 4 minus t squared dt, then f prime of x is just going to give you, well, the square root of 4 minus x squared. So what you're doing is you're taking the derivative of the integral. These are inverse operations, right? They're going to give you back the original function. So this will just give you f of x. Okay, so let's take a look at some different examples. Notice now your upper limits are not just the single x. This time they are a composition of function. This time it's x squared. Okay, so but we're still going to go through those two steps. So first thing, let's find the antiderivative. So this would be, let's see, step 1, t cubed over 3, evaluated from x squared to 0. Okay, so that's going to give me what? X squared cubed over 3 minus 0 cubed over 3, and so this is just going to give you x to the 6th over 3. All right, that's step 1. Step 2 is find the derivative of this, and so using the power rule, that's going to give you 6x to the 5th over 3, and this cleans up to 2x to the 5th. Now this does not look like our original function, but we can manipulate this a little bit. And so what I can do is I can factor out, and I'll explain this in just a second. If I factor out a 2x, that will give me x squared squared. So what we're getting here is, well, here's the upper limit. This is my upper limit, the x squared. My function is t squared, so I've got the upper limit substituted into the function. Now where does this 2x come into play? Well, it's the derivative of the upper limit, so we're using the chain rule here. All right, let's take a look at another example. All right, so step 1, antiderivative. So t cubed over 3 plus 4t squared over 2. Clean up just a little bit. T cubed over 3 plus 2t squared, evaluated x squared to 1. Let's see, I barely touched on the constant in the first problem, but then the second problem, I'm not even going to worry about that. I'm going to go ahead and substitute in the upper limit, so that's going to give you x squared cubed over 3 plus 2x squared squared. If I substitute in the x squared for this t here and square it. All right, and so if I want to plug in the 1, I could do that, but I'm going to be subtracting a constant, and when I take the derivative of that in step 2, it's going to go away. Okay, so let's take the derivative now. The derivative of the first term by using the power rule is going to give you 3x squared squared over 3 times the derivative of the inside function. Oh shoot, what I should have done is, let me back up just a minute, clean up first. All right, so I'm going to continue this before I do that step 2. So this first term is going to give you x to the 6th over 3 plus, and let me see, 2x to the 4th. I just want to make sure I have my notes right. And all right, yep. All right, so now this is the end of step 1. Now step 2. Here, I'll change I just want to verify, make sure I'm going in the right direction here. All right, so now we find the derivative of this. So this would give you 6x to the 5th over 3 plus 8x cubed. All right, so clean this up first before we can start making any guesses about what we're looking at. So this is 2x to the 5th plus 8x cubed. Okay, so just like in the previous problem, We multiplied by the derivative of the upper limit, so we know that the derivative is going to be the same, 2x. So first thing I'm going to do is factor out a 2x, and this gives you, what, x to the 4th plus 4x squared. Now, it's the function evaluated at the upper limit, so this is really 2x and then x squared squared plus 4x squared. Okay, let's see if we got that all. So we have 2x, that's the chain. Here's our function evaluated at the upper limit, x squared. And so our original function was t squared, and so here's where that t squared plus 4t, and our t just happens to be x squared. And so we're good here. And you can clean it up a little bit, but I'm going to go ahead and leave it just like this. All right, let's try one more, number 9. Go back to my blue. All right, so, and I'm going to go ahead and rewrite this as x to the 1/2. And so this is the integral from some constant to x squared of t to the 1/2 dt. All right, so first, the antiderivative. So that'll give me what? Step 1, t to the 3/2 over 3/2 or times 2/3, and then we're going to evaluate that from x squared to 3. And so if I plug in the x squared, it's 2x squared to the 3/2 over 3 minus, plug in a constant, and that's just going to go away later. Okay, so let me clean up just a little bit because I don't want to get a lot of numbers going on here. So let's see, 2/3 and then x squared to the 3/2. Well, that's just x cubed. Okay, so now we're going to, step 2, change colors, just so I follow my steps. Step 2 is find the derivative of this. So using the power rule, that'll give me 3 times 2/3, which will just give me 2x squared. Okay, so how does this one, how do we make it follow those rules? Well, this one's kind of tricky. We know that the derivative of the upper limit is 2x, so I know it's going to be a 2x something. Well, then that's just x, right? And it's the function evaluated at that upper limit. So what can I evaluate this function to give me x? Well, I can rewrite it like this, the square root of x squared. Tricky, tricky, but we'll learn. All right, one more problem. Let's go ahead and skip the step. Let's just go ahead and see if we can do this without those steps. So it is the function evaluated at the upper limit, so this is going to be sine x squared times the derivative of the upper limit. And there it is. That's all it is. All right, so without the 2 steps, let's just jump straight to these answers. And noticing that always our lower limits are constants. We will look at an example where they are not constants and we have to do another couple steps. And I'll show you that in just a minute. But it's just the upper limit, derivative of the upper limit, so it's going to be 2x, and then the function evaluated at the upper limit. Upper limit derivative times the function evaluated at the upper limit. Bypass those 2 steps, so it is the function evaluated at the upper limit times the derivative of the upper limit. So then in this case it would be 2x times f of x squared. Okay, doesn't matter what that upper function is as long as this guy is a constant. And so I guess I should go ahead and label this one as also a constant. So this is the f of g of x times g prime of x. And the order doesn't matter when you're looking at factors, so you can put the g prime first or second, doesn't matter. All right, so I'm going to give you just a couple minutes. Try these. I want you to notice the first column all has upper limits of x. Second column, a little bit more interesting. But take just 2 minutes to see if you can work through these, and then we will look at the answers. All right, so here they are. Hopefully you work through these. So in this first one, we just have x to the 5th. In the second one, x squared plus 4x. The third one, square root of x squared minus 1. The next one, x to the 3rd plus 2x minus 1. And the last one in this column is just tangent of 1 over x. That's when all of our lower limits are just constants, because when we take the derivative, they go to 0. All right, and in the second column, something a little bit more interesting. We know that the derivative is going to be 2x, so there's the 2, and it's just the function evaluated at that upper limit, and you can kind of clean it up a bit. Derivative of this guy will be 2x, function evaluated at the upper limit. Derivative would be 2x, and then function evaluated. Cleaned it up to 2x to the 7th. Okay, let's see. Function evaluated at the upper limit times derivative of the upper limit. And last one. So here's the rule, the shortcut rule. It's the derivative of the upper limit times the function evaluated at the upper limit. All right, so now let's look at a couple of graphical examples. Sorry, when I was working through these before, I had a few markings on them. All right, so let's take a look. It says let h of x is equal to the integral from -1 to x of f of t dt. So the derivative of capital H of x, h prime of x, is equal to, well, f of x. It's just the derivative of the integral. Gives us the function. So in problem 25 it says determine the x-coordinate of the relative max and minimum. And that's what you might have seen over here. We know when we're looking at the derivative, when it goes from positive to negative slope, we have a max. And when it goes from negative slope to positive slope, we have a minimum. And so when I'm looking on my graph, I'm going from negative, let me pick a different color that shows up, negative to positive. So I know right here at an x value at 0, at x equals 0, I have a minimum. And this is because f, which is the derivative of h of x, which is equal to h prime of x, and that is, which equals h prime of x, changes from negative to positive. And then over here at an x value of 6, we have a max because f of x, which is h prime of x, changes from positive to negative. So we know where these max and minimums occur. In the next question, it's asking us to define what those values are. Find that maximum value and find that minimum value. So let's fill in our chart to get these answers. So let me clear this up. And so in this first problem, it says we're looking from an x value of -1. Well, this is just the integral. Let's just evaluate these integrals. So h of -1 would be the integral from -1 to -1 of f of t dt. Well, from -1 to 1, that's just 0. That is no value. When your upper and lower boundaries are the same, that's just 0. Okay, so now let's evaluate the next one, h of 0. So I'm looking at the integral from -1 to 0, and you know the integral is just the area under the curve. And so from -1 to 0, that is this little triangle right here. And if I just find the area of a triangle, half base times height, that's going to give me -1. Okay, and now I'm just going to keep working down. My next integral would be h of 1. So that's the integral from -1 to 1. So I'm going to add in another 1, but this time these two areas are going to cancel out, and I'll have 0. Okay, keep working down. I'm just going to find the area. I'm going to add on. Let's see, I'm going to add on these two. And so then my next value on the table would be 2. And then I'm going to add on these 2 more. And so my next value on the table would give me 4. And then this nice rectangular section here, I don't have to do a whole lot of calculating. I'm going to add on couple more, and so this time our area on the table will give you 6. Now 5, we are adding a little trapezoid, so I'm going to have to do a little bit of calculations here. Oh, all right, so let's see. Well, actually, no, because this is 1 full, and this is a half. So how about 7.5? I didn't even have to do the trapezoid. All right, that really was nice and easy. And then I'm adding another half, so this is 8. And then I'm subtracting a half, so now I'm back down to 7.5. And then I'm subtracting another 1.5, so this gives me down to 6. Subtract another 1.5, so this is 4.5. And then subtract another half, so I'm back to 4. So I can see on my table that my minimum amount is going to be -1, and my maximum amount is going to give me 8. And those are exactly where I said they were going to happen. So the maximum value, max value of 8, and the minimum value of -1. Okay, let's take a look at some problems. These are not in your packet, so you might want to just stop and take a minute to write them down. G of x is integral from 2 to x of 1 over 1 plus t cubed dt, and it says to find g prime of 2. So it's wanting you to find the derivative of this integral and evaluate it at 2. Well, the derivative of the integral is just the function evaluated, the upper limit times the derivative of the upper limit. So in this case, I'd have 1 over 1 plus x cubed. Now we need to evaluate it at 2. And so that would actually just be 1 over 1 plus 2 cubed. 1 over 1 plus 8 is 1/9. That's not too bad. How about this one? Oh, this time boundaries are switched. We have the function as the lower limit. So, and it's just asking me to find the derivative of the integral again. So that's nothing too bad. We can handle that. But we are going to have to switch our boundaries. So this is going to equal -0 to, can I write this, x to the 1/2 sine t dt. I don't even know if I need to do that. Oh, I do, because I have to find the function evaluated at the upper limit. So this would be negative sine of x to the 1/2 now times the derivative of the upper limit. So this is what I was talking about. It's easier for me to see if it's in a rational form. So 1/2 x to the -1/2. Now I'm going to go ahead and clean this up just a little bit. Okay, so this is sine square root of x in my numerator. This with the negative exponent, I'm going to move to the denominator. I'm going to rewrite it like that. Oh, and don't forget your negative sign. All right, let's take a look at another one. Okay, this is the example that I want everyone to copy down, because this one has x terms as the lower and upper limit. Okay, so think of some interval from x squared to x cubed. There has got to be some constant in between here. And so we're going to use up the property where we're going from a to c. It's equal to the integral from a to b plus the integral from b to c. And this b value, that's going to be that constant that we're going to break up into two integrals. Okay, so hopefully you understood that. And so I'm going to go ahead and rewrite this. X squared to some constant plus that constant x cubed. All right, so now this first term, hopefully you recognize we're going to need to go ahead and reverse the boundaries. So this is going to be a negative. But now we're back in business. We just have two integrals to work through. All right, so now it's just going to be, well, taking the derivative, and so it's going to be the function evaluated at the upper limit times the derivative of the upper limit. The derivative of the upper limit in this first term is just going to be 2x, so it's going to be -2x, and then this is going to be times 1 over 2 plus t to the 4th, and so it's going to be 2 plus x squared to the 4th, and then plus, let's see, this time, excuse me, the derivative of the upper limit is going to be 3x squared. So that's what I'm going to be multiplying by. So I'm going to go ahead and combine it together. And then I'm going to evaluate the function at that upper limit. And then I will go ahead and clean up just a tick. So negative 2x over 2 plus x to the 8th plus 3x squared over 2 plus x to the 12th. Okay, now we're back to a graphical problem. The graph of the function consists of 3 line segments. If the function g is an antiderivative of f such that g of 2 equal 5, for how many values of c between 0 and 6 does g of c equal 3? Okay, so we know that g of 2 equals 5. Let's start with that. We need to figure out, well, what is the initial amount? So we can use the fundamental theorem to find that initial amount. So here's my integral from 0 to 2 of f of t dt. And using the fundamental theorem, the antiderivative says g is the antiderivative of f. So this is going to be g of 2 minus g of 0. Okay, and so, and the integral is the area under the curve. So the area under this curve, which is just right here, that's 2 units. Base times height divided by 2. So 2 is equal to g of 2, which is equal to 5 minus g of 0. So our starting amount, g of 0, is equal to 3. All right, so that's one, we're starting at 3. Okay, so let's add on some area. So if we start at 0, we have quantity of 3, and then we add these 2, so then we'll be at 5, and then we subtract these 2, right? So then we're back to 3, right? Because we're adding these 2, that would give us 5, and we're subtracting these 2, so that gives us back down to 3. So that's our second 3. We started g of 0 is equal to 3, and now g of, what is this, 1, 2, 3, 4, is going to give us some value at 3. And then let's see, we're going to subtract off, I don't know how much ever this is, but then we're going to add back value. And somewhere in adding back that value, we're going to have another interval somewhere here between, what is that, 5 and 6? And I'm not going to find the exact value, but I know that some value in between these two, between 5 and 6, I'm going to add some area to get another 3. So in this case, I will have 3 instances of having an area equal to 3. Okay, let's take a look at this next one. Let h be the function defined by this integral. H of x equals from pi over 4 to x of sine t squared dt. Which of the following is an equation for the line tangent? So when we're looking at tangent lines, we need, first thing we need a point, and second thing we need is a slope. All right, so first let's evaluate. Well, what is h of pi over 4? Let's find that point. So pi over 4 to pi over 4, oh, that's nice, 0. So there's always something nice in store for us. Now we need to find the slope. So we need the derivative of this integral, which is just the function evaluated. So my slope is just the derivative of the integral, which is the function evaluated at the upper limit. All right, so now we need the slope evaluated at pi over 4. So it's going to be sine pi over 4, and this is quantity squared. So the y value at pi over 4 is root 2 over 2. Squared is what? 2 over 4, which is 1/2. Now we can find our point slope. Y minus y1 is equal to mx minus x1. And find your answer. Okay, I think we have maybe one more example. The derivative of the function is continuous on the closed interval from 0 to 4. Values of f and f prime for selected values of x are given in the table above. If the integral of the derivative, so they just reversed this time. So the integral of the derivative is equal to the derivative of the integral. So then f of 4 is equal to what? All right, so 0 to 4 of f prime of t dt is equal to, well, f of 4 minus f of 0. If we know that all of this is equal to 8, and I don't know what f of 4 is because that's not on my table, but I do know what f of 0 is, and f of 0 is 5. That comes straight from your table. All right, so let's see, f of 4 is going to give me, well, 8 and 5, 13. All right, last one, I promise. Which of the following is an equation for the line tangent to the graph of this at the point where x is negative 1? Okay, so we need a point and a slope, and it's always so nice when they have the upper and the lower limits equal, because if you look on your integral, it's just going to give you, well, y equals 3. If you plug in y of negative 1, that just gives us 3. So now we need the derivative of this. So the derivative of the 3, the constant, will go to 0, but the derivative of the integral is the function evaluated to the upper limit, so that the y prime is going to give us e to the negative x cubed. And now we're going to evaluate that at negative 1. So y prime of negative 1 is equal to e to the negative 1 cubed. And let's see, negative 1 cubed is negative 1, so that's just e, right? Oh, did I drop it? Oh, what did I do? I dropped a negative somehow. Hold on, let me back up. Take a look at my notes. Oh, y prime. Hey, how about, let's see. Oh, I guess I forgot the chain rule. Dang. Should have had a negative on it. All right, sorry, my bad. So this is going to equal negative e. Now we can write our tangent line. So y minus 3 is equal to negative e x plus 1. And that's done.